Ever think about the motors that power pretty much everything around us? From your blender at home to the biggest machines in a factory? Well, the most common one is the asynchronous motor, and it works on a principle that feels a little bit like magic. It creates motion without its key parts ever touching. So how on earth does it pull that off? Let's decode it.
Right. This is the big mystery we're going to solve today. There are no brushes to wear down, no powerful permanent magnets doing the work. It's really just metal and coils of wire. So what invisible force gets this thing to actually spin?
The secret to its genius and its incredible durability, it all boils down to just two main parts. And once we understand how they interact, or more importantly, how they don't physically interact, the whole concept just clicks into place.
So, on one side, you've got the stator. That's the outside part that doesn't move. It's packed with wire coils, and its one and only job is to create a magnetic field. And on the other side, we have the rotor. That's the bit that spins. This design is called a squirrel cage, and it's literally just a super durable cylinder of metal bars. Notice how there's nothing connecting them. No parts are meant to touch, and that's the whole key to why these motors just run forever.
Okay, so a stationary part and a spinning part that don't touch. The bridge between them is the core idea that makes this all possible, a totally invisible, rotating magnetic field. And the really cool part, this powerful field is created without a single moving piece.
Here's the play-by-play. When we feed alternating current to those coils in the stator, each one becomes an electromagnet, pulsing on and off in a perfect rhythm. This doesn't just create a magnetic field, it creates one that smoothly rotates around the inside of the motor. And the speed of that invisible force has a name: synchronous speed.
I think this really captures the idea perfectly. You can think of this rotating field as the motor's invisible heart, pumping out a powerful rotational force. This is the energy that's going to get transferred to the rotor, all without contact. But how? Well, the answer comes from a fundamental law of physics, Faraday's law of induction. All it really says is that if you have a changing magnetic field near a piece of metal, a conductor, you'll generate an electric current inside that metal. This is the whole induction part of its other name, the induction motor.
So get this, as the stator's magnetic field is spinning, it's constantly sweeping across the metal bars of that rotor. Thanks to Faraday's law, this action induces a really strong electric current inside the rotor's bars. And what happens when you have current flowing through a conductor? It creates its own magnetic field. Just like that, the passive rotor has become an active electromagnet.
Okay, so the stator makes a spinning field. That field turns the rotor into a magnet, and then that magnet gets dragged along for the ride. It sounds simple enough, but this is where we get to the most important piece of the puzzle, and the reason it's called asynchronous. The rotor is always chasing that magnetic field from the stator. It's like a magnetic carrot on a stick. It wants so badly to catch up, but it's physically impossible for it to ever spin at the exact same speed as the field. It always has to be lagging just a little bit behind.
This difference in speed, this gap, has a name. We call it slip. Now you'd think slip is a bad thing, right? Like it's some kind of inefficiency or a flaw, but it's not. In fact, slip is absolutely essential for the motor to even work.
So let's just lay it out clearly. On one hand, you have the synchronous speed of the magnetic field. Let's call it ns. It's steady. And on the other, you have the actual speed of the rotor, nr, which is always just a bit slower. It's always playing catch-up. Okay, so this is the big aha moment. Why must it be slower? Well, think about it. If the rotor ever did manage to catch up to the magnetic field, then from the rotor's point of view, the field isn't changing anymore. It's stationary. And what does Faraday's law tell us? No changing magnetic field means no induced current. No current means the rotor loses its magnetism. And no magnetism means a turning force, the torque, drops to zero. That slip is what keeps the whole induction process alive. That's why it's asynchronous. They are literally, by design, not in sync. So now that we've got the principle down, let's get a little more practical. We can actually calculate the theoretical top speed of that magnetic field, the synchronous speed, with a really simple formula. The speed of that magnetic field, Ns, really just comes down to two things. First is F, the frequency of the AC power we're feeding it, and the second is P, which is about the physical construction of the motor, how many magnetic poles are built into the stator. That's it. Those two things determine the speed.
But hang on a second. Look at that formula. What's up with the number 120? Physics formulas don't usually have these random numbers just tossed in. So where does that come from? Well, it's not a magic number. It's actually two really logical numbers put together.
The first part of the puzzle is the number 60. See, the frequency, F, is measured in cycles per second, or hertz. but we want our motor speed in revolutions per minute. So to convert from seconds to minutes, we just multiply by 60. Simple enough?
The second piece is the number 2. Every magnet has to have a north pole and a south pole, right? So for the magnetic field to complete one full rotation, it has to pass a pair of poles. The formula has to account for this pairing. So what's 60 times 2? 120. See? It's just unit conversion and basic physics all rolled into one tidy little number.
All right, now that we've totally cracked the formula, we can see exactly how we can control the motor speed in the real world. The answer is sitting right there in the equation.
So if we look at our formula, ns equals 120 times f divided by p, there are really only 2 knobs we can turn. We could change p, the number of poles, but that's physically built into the motor, so that's not happening. Or we could change f, the frequency of the power going into it, and that we can absolutely change with electronics.
And we do it with a device called a variable frequency drive, or a VFD. Think of a VFD as a sophisticated controller that can take normal power from the wall and spit it back out at any frequency we want. By tweaking that F value up or down, we get incredible, precise control over the motor's speed.
And having this level of control is an absolute game changer for energy efficiency. Think about giant industrial fans, or pumps, or conveyor belts. They don't always need to run at 100% speed. A VFD lets the motor run at the exact speed needed for the job, and that can cut energy use by 30% or even more. It's a huge deal.
So when you put it all together, you really see why this motor design took over the world. It's brilliantly simple. With no brushes to wear out, it's incredibly durable and lasts forever. Then, when you pair it with modern electronics like a VFD, it becomes incredibly efficient. That mix of toughness, efficiency, and elegant design makes it the workhorse that powers our modern life.
From a powerful force created by invisible fields to a flaw-like slip that turns out to be its biggest strength, the asynchronous motor is just a masterclass in elegant engineering. It makes you wonder, doesn't it? What other complex problems out there are just waiting for a beautifully simple solution like this?